This is the grand finale of this year, RSA Encryption, and if you're waiting until the last minute, like a week from now on a period 5 or 7 to finish this video, you're going to be spending a lot of time either just wasting it watching us do stuff or not trying it yourself. Because one of the big points of this is that if you're going to factor large composite numbers without technology assistance, it's going to take you some time, and even with technology assistance, when the number gets large enough, it still takes a lot of time. The first example is to factor 11,524, and you can see that that's divisible by, well, 2 for 1. And if you're trying to factor, you just want to be efficient about it. Just take this number and start to divide it by things that you know are going to work. So I'm going to take 11524, divide it by 2, and this is with technology assistance. I get 5762. Then let's divide that by another 2, and end up with 2881. Now, 2881, if I want to figure out if that number is prime or not, I have to test all the prime numbers up to the square root of 2881. So I'm going to take the square root of 2881, and I actually do this a lot when I have race numbers. I want to see if they're prime. It's just kind of like a compulsion of mine. And I end up with 53. So I have to test and go 2881 divided by, I know that 2 plus 8 plus 8 plus 1 is not divisible by 3, so it's not divisible by 3. And keep moving up, not by 5. I can try 7. I can try 11. And I have to keep going up and test, and there's no shortcut around this. You have to test every prime number up to the square root of 53. So if I keep moving up, I can try 17, and I'm going to encourage you to pause this video, just keep punching this in a little bit faster, and try to find what the factor is. So I got 23, not 25, not 27. Could try 29. Divided by 29. Nope. 2881. A lot of people just give up and say it's prime here because we're at 31. I can try 37. 2881. I know 39 is not prime. 41. And then 2881 divided by 43. Boom, got it. It's actually 43 times 67. And we would not have known that unless we had had the diligence to work all the way up and see that. So if I keep trying some other ones and trying the prime factorization with 1119672, let's see, 1119672. I can divide by 2 until I can't anymore. Okay, now I can't. Check the sum of digits. That is divisible by 3, so let's divide by 3 until I can't anymore. Okay, I couldn't there. And I have 15551. Now, if you have the Inspire CAS or any computer assisted program, and you can find these on the internet too, you can look to see, Wolfram Alpha will also do this, if you can factor a number. So I'm going to try to factor 15551, and it just shows 15551. So that's prime. So I divided by 2 3 times, and 3 2 times, and then 15551. Now, we get to a larger number. This one, which is, let's see, that is 3,453,389,167. And if I want to try to factor that, so let me just type in factor. With computer assistance, 3,453,389,167. It spits out through two numbers, or two. Yeah. I'm trying to see if that's the right number. That's different than what I have. Let me pause this for just. Nope, that's right. So that is 34539 times 99991. And so then the last one, if I want to do this with computer assistance, I'm going to plug that in, and I'm going to tell you that this one is prime. And the only way to know that is to actually just go through and try the numbers up to the square root. So how many possibilities are there? You test every prime up to radical whatever the number is. So that's a lot of numbers to test, and that's something that's going to be very, very difficult for you to figure out. how you're doing. So basically, this fact that factoring large numbers is huge. This fact is something that is the essence behind bank encryption and internet security. Because if I start plugging in lots and lots and lots of digits, it's going to get to a point where if I press enter, not there yet, but all I have to do is just tack on more zeros and I start to compound this greatly. Let's put in some more zeros and just some other numbers and keep doing that. Eventually we're going to get to a number that is so large that the calculator and the computer can't handle it. And I think I'm already there. I pressed enter and the computer seems to be, well, we'll let that think for a minute. So the key behind encoding and taking your information and encoding it is this. If you want to encode information, what you do as the owner of this system is you find two huge prime numbers. And when I say huge, I mean 400-digit prime numbers. So a 400-digit prime is going to be larger than any organization could ever factor. And what I know is that a 400-digit prime, like a 10 to the 400th number, is going to be equal to two 10 to the 200 digits numbers. So let's back up. We actually don't need a 400-digit prime. We just need two 200-digit primes, which we're going to multiply and make a 400-digit composite number. So let's erase this. We've got two 200 digits. Find two huge prime numbers, multiply them, and this thing you release. You release the product of the two prime numbers out into the public, and you can use that to encode the information. But in order to decode it, you needed to know what the original two prime numbers were. And the only way to know that is just to know it, because no computer on Earth or even beyond can ever do it. And if 200 digits is not good enough, make it 250 digits. Now you've just encompassed the entire combined computing power that's ever happened in the history of time. And if ever there does become better computing power, just keep going up in the prime numbers. Just keep going higher and higher. So prime numbers then become extremely valuable. In fact, you can make upwards of $1 million by discovering a new 200-digit prime number and proving that that's prime. And if it's a number that hasn't been classified as prime before, you can. So again, you release the large composite number n, and this is what you use to encode, and that's public. And this is what the P and the Q is what you use to decode, and that's private. You don't know that unless you're the actual original owner. So the way you do this is you have to choose another number e. We're going to practice this. That is relatively prime to p minus 2 or p minus 1 times q minus 1. This means no common factor. Then you release that number and n as the public key. So this is the public part, accessible by anybody who wishes to encode the message. You use that to translate your message into an integer string, and you're not supposed to include easily decipherable phrases or pieces. This is just part of basic code breaking. It's supposed to just be something simple but not predictable and not repeatable. For instance, don't use a lot of ands or thes or other words that would be obvious. And once you translate that, you let that be m. This is your message, and that's what the m means. You know the message, but then you calculate m to the e mod n, and you get this c, and that's what you transmit over an open line that anyone can see. Once the person on the other end gets c, you decode it. You decode it by finding a number d such that ed is equal to 1 mod p minus 1 q minus 1. So you have to know p minus 1 q minus 1. You have to know what those are. Then you do this calculation, c to the d mod n, and you get a result that is actually m to the e to the negative 1, which is obviously equal to m. So I know this is very, very confusing right now, but let's just practice an example, and we'll do this. So this is a very simple example. I'm giving you the numbers here to use. So again, I'm giving you the message is 35. We don't know what 35 means, but that's your message. Sorry, I'm looking down here. Your your multiple, your composite number is n, and your e. And remember, this e is relatively prime to p minus 1, q minus 1 is 7. So you can kind of go through and see, is that actually true? well, here's what happened. Person A selected 2 primes. Sorry, just checking time. And that was P is equal to 23 and Q is equal to 41. So then we know that that N was 943. So that's where that came from. Then person A chooses E, which is relatively prime to P minus 1 is 22, Q minus 1 is 40. If I multiply them together, I get 880. All I need is a number that's not divisible by 880, or that doesn't divide 880. Give me a number that doesn't divide into 880. 7. So we're going to let 75. E equal 7. Typically, the smaller the number, the much easier this is. So you want to use numbers like 2, 3, 5, 7, wherever possible. So we have E is equal to 7, and we release 7943 as the key. And that's what's used to encrypt it. Next, I'm going to switch colors. Person B has a message to send to A. And we can say that message is CE. Person B wants to send the message CE. So we're going to take that. C is the 3rd letter of the alphabet, E is the 5th letter of the alphabet, and as we're going to say that M is equal to 35. So person B has to take 35 and convert that to something else in order to transmit it on an open line. So person B calculates C is equal to M to the E mod N. So M is 35, 35 to the 7th, and I want to do that mod 943. Well, if I look in the calculator, 35 raised to the 7th power is this. And if I want to figure out what it is mod 943, I need to figure out what its remainder is when I divide it by 943. So 943, Control Enter. Oops, I want to get that back again. Sorry. That's better. So that's a little much. Your calculator actually includes a mod operation, which might be easier and better on you to use. There we go. Found it. So I have 35 to the 7th mod 943, and that gives me the message 545. So we're going to go back to person A, who has that. Person A receives 545, and then we look at what person A has to do. Find a number D such that ED equals 1 mod. Okay, so if I find a number D such that ED is equal to 1 mod P minus 1 times Q minus 1, which was 880 from above. Actually, I'm going to write the P minus 1, Q minus 1 here. So I have ED is equal to 1 mod 880. Basically, I need to find a number so that 7D is equal to 1 mod 880. The way I kind of think about this is I need to find some number so that if I were to take 880 times that number and add 1 and divide it by 7, I would get an even number. So we can start to play around with that. What's a number that I can multiply 880 by? And you can start playing a guess and check, or plus 1 or times 1 times 2 times 3. It turns out that actually 4 is going to work. So I have 4 is equal to question mark, and if 4 is equal to this question mark, that's going to tell me what D has, or not what D has to be. That's going to tell me what what D could be. So I go 880, oops, let's get the right colors, times 4 plus 1 over 7, and I get 503, and that should be what D is. So 503 is just one possible D. And then finally I'm going to calculate C to the D power mod n. So 545 to the 503 mod 943. Now, you guys have a calculator, and again, to do this, we would just go to the calculator and type in MOD 545 raised to the 503, and then do comma, and you want NOD 943. And it's beyond the limits of what the calculator can do. So we need a way around this, and we do. If your calculator screams at you and says you can't do this, what we want to do is we want to break down 503 into a series of smaller numbers. So this is what I'm going to do. I'm going to say 503, the exponent, and I'm going to break it down into powers of 2. It's equal to 256 plus 128 plus 64 plus 32 plus 16 plus 4 plus 2 plus 1. That's not every power of 2 in there. I skipped 8, but it's most of them. So we're kind of looking to see how I can break this down, and what I'm essentially saying that is that 545 is equal to the 503rd is equal to 545 to the 256 plus 128 plus 64 plus 32 plus 16 plus 4 plus 2 plus 1. That's not too hard to figure out. But that means that this is 545 to the 256 times 545 to the 128 times 545 to the 64th times 545 to the 32nd times 545 to the 16th, 545 to the 4th, 545 to the 2nd, sorry, I'm running out of space here, and then times 545. Sorry. There we go. Well, basically I'm going to take each of these numbers and replace with what they are, mod 943. 545 is 545 in a mod 943 world, because it has not reached 943 yet. Then I'm going to do 545 squared and see what that is, mod 943. And if I do 545 squared 943, 545 squared is 29705 mod 943. And if I see what the remainder is when dividing by 943, it's 923. So this gets replaced by 923. Then what I'm going to do is use the fact that I knew that to figure out what 545 to the 4th is. 545 to the 4th mod 943 is equal to 545 squared mod 943. Well, I said 545 squared was 923, and 923 squared mod 943 is a smaller operation. And if I figure out what that is, that's 400. So then I start working my way left and say that this is 400. Then I keep going. We're going to go 545 to the 8th. Now, even though I'm not substituting that, I need that to build what 16 is. So 545 to the 8th mod 943 is 545 to the 4th squared mod 943. And 545 to the 4th is 400, so I have 400 squared mod 943, and that is going to be, let's see, that's going to be 633. So if you keep that recursive process going, you're going to get 545 to the 16th is equal to 857. 545 to the 32nd is equal to 795. And I'm going to start writing these up here. You get 857, then you get 795, and then you get 215, and then you get 18, and then finally you get 324. And if you multiply all these out, which is a lot smaller for a calculator to do than what the originals were, if you multiply all of those out and then take it, it's equal to 35 when you do it mod 943, and that gets your original 35 message back. Now clearly there are computer programs that will do that much faster, but given that this is just a few problems, that's the process. So that's what happens when you have this where the calculator is going to spit out infinity because it just can't do 545 to the 503. But if you think about it, in a mod 943 world, we should continue to be able to do and reduce them down and make them smaller and smaller and smaller so we can multiply them all out. Good luck. This is a tough one.